A sequence is a list of terms, but when we add those terms together, we get what is known as a series. In order to specify the addition of a sequence, or to summarize it, we have summation notation or sigma notation. So that's what you're seeing down below. It's this weird E looking thing. It's actually the Greek symbol sigma, or the Greek letter sigma. And we use that to show the summation or the addition of all the terms in a given sequence. So if I give you a sequence, A1, A2, A3, A4, and so on, we can write it as the sum of the first n terms of the sequence using the expression that I have below. Now you see the symbols, but in words it's read as the sum of AK, that's your sequence, or that's how you generate the terms of the sequence, from k equals 1, which is known as your lower bound, and you can see that that's on the bottom of the sigma notation, to k equals n, which is known as your upper bound, which you can see is on the top of your sigma notation. So this would be if I did A1 plus A2 plus A3 plus, and so on, all the way until AN, because that's where it told me to stop. So that's just kind of what the notation looks like, but we are going to take a look at some examples, and it'll make more sense as we go through the examples. So example 1, this says 3 times 2 to the k minus 1 from k equals 1, because remember, this down here is my lower bound, or my starting term, and then this 7 up here is the upper bound, or my ending term. So if we want to go back, we can add that to our previous slide where we took those notes. I can say that my lower bound over here is also my starting term. And then my upper bound over here, I don't know if it's going to fit. Let me scroll down a little bit. My upper bound is also going to be my ending term. Okay. So I'm going to substitute to generate the terms of the sequence. So I'm going to start with 1, and I'm going to go all the way until I get to 7. So 3, 2 to the 1 minus 1. That's my first term. I'm going to add that to the second term, which would be 3 times 2 to the 2 minus 1. Then I'm going to add that to the third term, which would be 3 times 2 to the 3 minus 1. Now, if you notice, all I'm doing is substituting for k to find the terms of the sequence. And I'm going to keep doing this over and over and over again. But I'd have to substitute 7 times. I'd have to type into my calculator 7 times. So then I'd have to add them all together. So we're going to do a little bit of a shortcut here, and we're going to use the calculator to generate the terms of this sequence. So in order to help us, what we're going to do is we're going to go in our calculator to y equals, and I'm going to type in 3 times 2 to the x minus 1, and I'm going to copy down the terms from 1 all the way down until I get to 7, because that's my ending term. And then okay, so as I said, I'm going to go to my y equals, I'm going to type in 3 times 2 with an exponent of x minus 1. Now I have an older version of the calculator, so I need to use parentheses, but you shouldn't, because it should come up in the exponent spot for you as a superscript. Then I'm going to go to my table. So second graph will bring me to my table, and these are my terms of the sequence. So the first term of the sequence, if I were to evaluate in the home screen, would give me 3. The next term would give me 6, 12, and so on. So these are going to be the terms that I'm going to add together. So my first term is 3, 6, and so on. So instead of evaluating all of those, I'm going to substitute them all. So it's going to be 3 plus 6 plus 12 plus all the way until I get to the 7th term. So I'm going to go back to my calculator. 24, 48, 96. And then I'm missing one more, so I'm going to go back to my calculator again and scroll down until I get the 7th term, which is 192. So that's the shortcut for you. Instead of evaluating in your home screen of the calculator, you can use the y equals if you'd like. So now I'm going to add all these together. So I'm going to go into my calculator. I'm going to quit where I'm at and go to the home screen. And I'm going to type in 3 plus 6 plus 12 plus 24 plus 48 plus 96 plus 192. So my sum is 381. And that's my answer for this summation question back at the top. So here, I wrote it all out in red, but that's really equal to 381. So I'm going to show you one more that I want you to try on your own, and then I'll go over it. So here's the next one. You're going to find the summation of 3x squared from x equals 2 to x equals 4. So you can use the shortcut on your calculator, or you can substitute and then add them all up. It's up to you. So pause the video at this point, try it on your own, and then hit play, and it'll be shown and you can check your answer. So here's the answer shown out. This is what you should have. So in the red, I did it by substituting. I substituted starting with my lower bound, x equals 2, all the way up till my upper bound of x equals 4. I evaluated each one of them, and then I added. Or in the blue, I did it as a shortcut using my calculator. I typed in 3x squared into the y equals, and then I went to my table, I found the second term, the third term, and the fourth term, which were the same as when I evaluated, and then I substituted in that way. So now let's take a look at how we write the summation. So this time I'm giving you the terms of the sequence, as you can see, all outlined here for you. 40 plus 40 times 1.005 plus 40 times 1.005 squared, all the way up to 40 plus 1.005 to the 11th. So the steps for writing a summation are to write the explicit formula for the sequence, and then you're going to put it into sigma notation using your upper and your lower bounds. Now, most of the time when you're writing the explicit formula, it's going to be geometric. Now, whether it's geometric or arithmetic, remember that it's on the formula sheet or on the reference sheet. So this happens to be geometric because I'm multiplying every time. So my sequence, whoop, is going to be AN is equal to A1R to the n minus 1. Remember that A1 is your first term, R is your common ratio, and then n minus 1 is your term number, minus 1. So I have AN equals, my first term is 40. What I'm multiplying every time by is 1.005, and then I have n minus 1. So that's my sequence. But now I need to put it with the sigma notation. So I'm going to put it right next to it. I just need to decide on my lower bound and then my upper bound. So if I look at the sequence, the first term in the sequence is 40. So if I start with n equals 1 as my lower bound and I were to substitute in, I could check it out to see if it works. So here's your check. 40, 1.005 to the 1 minus 1, that's going to give me 40. You can check that on your calculator if you want. So that means I started with my lower bound correctly. Now I need to determine what my upper bound is. So if I'm starting at 40 here, I'm going all the way to when there's an exponent of 11. So I need to go all the way to 12. And once again, you can check if you want by substituting. So if I check down here and I substitute 12, I would have 40, 1.005 to the 12 minus 1, which gives me 11. 40, 1.005 to the 11th, which is my last term that they gave me. So that means that if it lets me scroll back up, there we go. That means that this is the sigma notation that would give you or generate that sequence that they gave you up top here. Let's do one more together and then you're going to try two on your own. Given a geometric series defined by the recursive formula a1 equals 3 and an equals an minus 1 times 2, write the equation for the first 5 terms of the series using sigma notation. So I need to find these terms. Well, remember that a1 is given as 3. To find a2, it's recursive, so I need to multiply by 2. So a2 is going to be 3 times 2, which gives me 6. A3 is going to be 3, I'm sorry, not 3 times 6. That's the wrong formula. They were telling me to do the previous term times 2, so it's going to be 6 times 2. So let's change that. I should have set this up how I always do. So it's going to be 6 times 2, which gives me 12. Then to find a 4, it's going to be 12 times 2, which gives me 24. And then the fifth term is going to be 24 times 2, which gives me 48. So the terms in my sequence that I have to write the notation for are 3, 6, 12, 24, and 48. So remember, your first step is to write your sequence notation. So an equals a1 r to the n minus 1 power. So an, my first term is 3. My common ratio is 2 because that's what I'm multiplying by each time. And then I have n minus 1. So that is my sequence. Now I'm going to put it with sigma to make it the summation notation. So sigma of 3, 2 to the n minus 1, and I need to determine my upper and lower bound. So my lower bound is going to be 1, and my upper bound is going to be 5 because it's the first 5 terms. So the first term, the second term, third term, fourth term, and fifth term. So there's your answer. So now what I'd like you to do is I would like you to try the next 2 examples on your own and hit pause, give them a try, and then hit play to check your answer. So hopefully you tried these on your own. So here are the answers. For number 1, my sequence was 12,000 times 1/10 to the n minus 1. So when I put it in sigma notation, my lower bound was n equals 1 and my upper bound was 10. Now, instead of 1/10, if you put 0.1 to the n minus 1, that would be okay as well. And then number 2, my sequence was 3 times -4 to the n minus 1. Be careful because it had to be a -4 because your sign was changing to get from term to term. So each time you're multiplying by -4. So that was your common ratio. And then when I put it in, it wanted the first 8 terms. So my lower bound was n equals 1 and my upper bound was 8. So that's how you evaluate sigma notation, and how you write a series or a sequence represented in sigma notation. So hopefully that was helpful. And if you have any questions, be sure to ask them in class.